The question says define conductivity and molar conductivity for the solution of an electrolyte. Also discuss their variation with concentration. Let's take a look. First of all, if you're trying to measure conductivity of any solution, how exactly are you going to determine that? Well, by passing current through a solution. And if you're trying to pass current through a solution, how exactly you would be able to pass a current through a solution? Well, it is usually done in very specific equipments. Okay, and we have a cell or an apparatus for measuring this conductance. How is it? It's usually made in the form of a cube. Well, a cube or even a cuboid for that matter is okay. This is the way, right? It could be very well a cuboid, no issues. There is some area of cross section here. Yes. Same area is on the side, of course. Yes. And there is some separation L, length L, in between these two parallel opposite phases of the cuboid. Of course, yes. Now what do? I fill up this cuboid with the solution for whom I have intentions of making conductometric measurements. I fill up this. Fine. What else? And then this side and this side both are connected to some kind of a cell. We pass current. And as we try to pass current by various methods, we could actually make measurements. For example, by using Wheatstone's bridge, we could make measurements of what is the resistance of this solution. You remember in physics, we talked about resistance, yes? And we said that this resistance R is directly proportional to length of conductor. And in this case, it will be the distance between these parallel plates L. And it is inversely proportional. By experiment we can find it is inversely proportional to area of cross section, and this is in this case the area of cross section. So we say R is equal to rho L by A. This is what physics people used to say. In chemistry, we just take 1 by rho is 1 by R L by A. R is resistance, so reciprocal of R is defined as G, which is conductance. L by A is called, of course, cell constant, and 1 by rho is denoted by a Greek letter kappa, and kappa is called specific conductance or conductivity. So what is conductivity? We have just managed to derive also, although this was not asked, but just to explain you, I just needed an excuse to make an explanation because students usually find this tough. It's very, very easy. Kappa is GL by A. How do we in words define this? We say conductivity of a solution is defined as conductance of a solution. It is defined as conductance of a solution placed in a conductometric cell having unit area of cross section, having unit means 1, having unit area of cross section separated by a unit distance. So let me repeat, what is conductivity kappa? Conductivity is defined as the conductance, G is conductance, so it is the conductance of a solution which is placed between two parallel plates having area of cross section unity separated by unit distance. That's it. And of course, what are the units? We must write down units also. Units of kappa are Simon per meter or Simon per centimeter, or Simon is per ohm per meter or per ohm per centimeter. Please remember, these are SI units, and since 1 Simon is 1 per ohm or 1 mho, these are identical units. Right? So this is about conductivity. What about molar conductivity, lambda m? What is that? That's also very simple. Molar conductivity, which is also denoted by lambda m, it is the conductivity of a solution. It is the conductivity of a solution which contains 1 mole of the electrolyte. Conductivity of a solution containing 1 mole of electrolyte. When filled between parallel plates separated by unit distance. When filled between parallel plates separated by unit distance. Please note that in case of lambda m, area need not be unit area, of course, obviously. Why? Because you have to add enough solution so that it contains 1 mole of electrolyte. Right? What are the units? Units for lambda m are Simon meter square per mole or Simon centimeter square per mole. They look ugly, don't be bogged down by this. The simple expression. Is there a relation between kappa and lambda m? Yes, there is. Although this is not asked, but just let me mention, lambda m is kappa by c into 10 is to 3 if centimeter, CGS units are used. Okay. And in case SI units are used, instead of 10 is to plus 3, it becomes 10 is to minus 3. This is just a formula. If you have this, great. But again, this is not a part of this question, but we'll be using this very often, so I just happen to mention this. If you are just supposed to answer this question, I have answered this already. Last part. Discuss their variation with concentration. That is very simple. Let me say, as concentration increases, kappa increases. As concentration increases, you find conductivity increases because within the same solution you have more ions, so they can carry more current by common sense. But as concentration increases, you find lambda m decreases. Molar conductance decreases, yes. Molar conductance decreases, and there is an equation also which is called Kohlrausch law. Lambda m is lambda m naught minus b root c. Although this is not really very much a part of this question, but then the variation with concentration has been, it was discussed by Kirchhoff and later on it was refined also. Now this is more called Debye-Huckel-Onsager equation. Don't worry about names much if they sound very bad to you. Lambda m versus concentration, this is the way you write it down. Lambda m naught and b are constants. Concentration c is a variable and lambda m is a variable. So as you can see, concentration increases, lambda m decreases.